Every so often they send these emergency alerts with these phones that are constantly encroaching on our freedoms. I'm getting a little sick and tired of it. This fake pandemic. So H is the enthalpy change, which is a measurement of the heat that's exchanged in the reaction. And E is the internal energy. So that's all the energies contained in the molecule, some of which can't be measured easily. So what they measure is just the heat output, and then they can, by inference or by subtraction, find out what the internal energy of the molecule is. So internal energy is E. P is the pressure. And delta V is the change in volume produced by the expanding gas. So, of course, for a gas to do work, it has to expand against something. So if you think about your car engine, what happens inside your car engine? You have gas being pumped in the form of a vapor, gasoline, which is a hydrocarbon. And then once a certain amount of the hydrocarbon has been pumped in, it swirls inside the combustion chamber, mixed in with air, which contains oxygen, and then the spark plug makes a spark, and it causes that mixture to explode. And during the explosion, the piston gets pushed down inside the engine, and that's connected to the other mechanical parts of the engine. It transfers that explosive power into rotary motion. So we're harnessing the expansion of the gas to do work. But what would happen if the engine couldn't do work? Say you had the injection of the fuel, the spark plug explodes, and then the piston just stays put. So it doesn't move. So the explosion takes place, but the piston doesn't move. So all that energy that was contained within the gasoline exploding is now confined within the walls of that container, but it's not allowed to do any work. So what happens? The temperature of the system goes up. So all the energy that would have come out as mechanical energy gets turned into extra heat energy, and that's what we do when we use a bomb calorimeter, which I'll mention later. So since gases do work by expanding, in atmospheric pressure. So when a chemical reaction produces gas, those gas molecules coming out of the reaction surface, they have to push other air molecules out of the way. That involves doing work. And the higher the air pressure that the reaction is exposed to, the more work has to be done by the reaction to push the air molecules out of the way. If you did a chemical reaction on the surface of the moon where there's no atmosphere, there would be no PV work because the gas doesn't have any pressure to expand against. It would go into the infinite volume of space, but because it encounters no resistance, it does no work. So to do work, one of two things has to happen. Actually, both of two things have to happen. There has to be some kind of resistance, and there has to be movement. And I'll give you examples where you could have a huge amount of pressure but no movement, no work gets done. So a bridge sitting on a pillar, there's maybe 20 tons of pressure on the pillar, but because the bridge isn't moving, no work is being done. Likewise, you could have a very heavy object drifting through space, but because there's a vacuum in space and there's no resistance to its movement, the object is doing no work. So to do work, there has to be resistance and there has to be movement. Otherwise, you don't fulfill the conditions for the doing of work. Work done by a gas is defined by the following formula. P delta V. So work is equal to negative P delta V. W equals work. P is equal to the pressure that the gas is working against, and delta V is the volume change of the gas. So if we know that the internal energy of a chemical substance is given by E is equal to Q plus W, and we know that the work done by a gas is P delta V, we could substitute into the definition for enthalpy. And you get, so enthalpy is equal to the internal energy plus the P delta V work. And we're going to replace E with a Q plus W. And we're going to replace the P delta V with negative W. See, take the negative sign there and put it over here. Negative W is equal to P delta V. So you could put negative W here inside the bracket. When you add that all up, you got Q plus W minus W. Well, what that gives you is H is equal to the heat. The enthalpy is the amount of heat that is evolved if you carry out the reaction at constant pressure. This is why when they do bomb calorimetry, what do? They keep the reaction confined into a container. So what they do is they have a container made of 1/4 inch thick steel with a big heavy screw top. So for example, say if you wanted to find out how much energy was contained in your breakfast cereal, they would take maybe 10 grams of your breakfast cereal, put it inside this steel container made of a heavy wall of stainless steel so that it's not going to actually explode. They call it a bomb calorimeter, but it doesn't actually explode. The explosion takes place inside there, but it's all contained within the strong walls of the bomb calorimeter. They take that whole assembly, they screw on the big heavy lid, they have a thermometer inserted, they have a special spark plug inserted into it as well, and then they pump it full of pure oxygen. I think they go up to about 35 atmospheres of pure oxygen. Then they take that whole assembly and they put it underwater in a big tub. And then they make the spark go. And the spark plug ignites the cereal or whatever food stuff is contained within the bomb calorimeter. And all of the stuff in there burns completely to a crisp. All the cereal completely burns to a crisp, releases all of its energy, but only in the form of heat. Why? Because it's not allowed to do work. Remember, the definition for work is that there has to be movement. The gas is not allowed to expand. Okay, it expands within the tiny confines of the bomb calorimeter, but strictly speaking, that's a negligible amount of expansion. So all that energy that would have gone into doing physical work is now converted into the rapid motion of the air molecules inside the bomb calorimeter, so it all turns into heat. So all the energy contained in the food turns into heat, and by measuring the temperature change of the water in which the bomb calorimeter is immersed, you can get a measure of the value H. And then if you do the same experiment open to the air, the difference in measurements is going to tell you the P delta V part, so you can easily find out what the internal energy is by subtraction. Okay, so that's how that works. H is equal to the heat flux at constant pressure. You do the reaction translation. A reaction conducted at constant pressure reveals the enthalpy content of a chemical substance. You might ask yourself, well, how is this constant pressure taking place? Because in a bomb calorimeter, the pressure suddenly goes up. Well, what happens is they measure it after the reaction. After the reaction, the pressure in there is higher because everything has been consumed and burned, and the energy of the air molecules in there is rapidly increased. But that, after it sits there for a second, the pressure stabilizes. After the reaction is over, it sits, and it's at constant pressure. So then all that extra pressure is really the work trying to get out, but it can't because it has nowhere to expand to. So it basically turns into a temperature increase, and that resultant temperature increase is measured as enthalpy. The internal energy can be calculated by allowing the gas to actually do work. And measuring that, and then subtracting it. All right. Just wanted to show you something about the units here. If you look at the internal energy, if you look at this part here, the P delta V, pressure is defined as the force applied over area. And that's multiplied by volume. That's what P delta V means. And if you were to look at the units of force, it's newtons, and the area is given in meters squared. Volume is always given in meters cubed. So if you multiply this out, you're going to cancel meters cubed with meters squared, and what you're going to be left with is Newton meters. And Newton meters is units of joules. So that's work. That's the units of work. So the units work out when you look at them. So what would I like you to do today? Watch and make notes on part 5 of my Thermodynamics playlist. And let me see if I can find you a nice, juicy calorimetry problem. To add. Wait, I can give you this. Too bad I don't have the blank version of it. Let me see. I have another one. And you don't have the textbooks yet, so I can't give you problems out of that either. Well, I'll just do a simple calorimetry problem with you to show you how it's very introductory to this. This is just measurement of heat flux, but you got to start somewhere. Don't fall behind, guys. Watch those videos and make notes, or else before long, it's going to seem like I'm speaking Chinese to you. Okay, you need to keep up. And if you're Chinese, it'll look like I'm speaking Greek. So choose your language. Heated bricks. Or blocks of iron were used long ago to warm beds. In the old days, in fact, people used to keep barrels of water in their basement. And what that would do is during the day, the barrels of water would warm up, and they would absorb heat energy. And then at night, when the ambient temperature dropped, those same water barrels would release the heat energy into the environment, and they would help modify the temperature jumps between night and day. The same concept is what moderates the weather in Toronto. If you go to Montreal, which is essentially at the same latitude as Toronto, the winter weather in Montreal is far worse than it is in Toronto. And why is that? Because we're close to Lake Ontario. So Lake Ontario, during the day, it absorbs heat from the sun, which helps to moderate temperatures in the summer, because the cooling effect of the lake during the day. And then at night, when the ambient temperature drops below the temperature of the lake water begins to release energy into the environment, so it tends to make the nights balmier. And so it has the effect of moderating temperatures. Whereas in Montreal, because there's no Lake Ontario, you only have the Lake St. Louis, which is a tiny lake by comparison, the lake effect is much weaker. And so you see bigger temperature differences between Montreal and Toronto. So we benefit here in Toronto, we benefit from the lake effect. Montreal, not so much. And the winter temperatures in Montreal tend to be about 5 degrees cooler in my experience. I remember standing at the bus stop when I was in high school wearing tight jeans and thinking to myself, oh, this was a mistake, and wind whipped, especially if you have one of those bus stations with no shelter. It gets pretty cold. So anyway, heated bricks or blocks of iron were used long ago to warm beds for the advent of thermostats and forced air gas furnaces. A 1.49 kilogram block of iron heated to 155 degrees Celsius would release how many joules of heat as it cooled to 22 degrees Celsius. If it took half an hour to do so, what would the wattage be? So I just threw in a little extra in that question because it's an easy question. By the way, the specific heat capacity of a block of iron is 0.4494 joules per gram degree Celsius, meaning that for every 1 degree drop in temperature for a 1 gram piece of iron, it would give off 0.44 joules of energy. Or if you wanted to increase the temperature of a piece of iron weighing 1 gram by 1 degree Celsius, you would have to input that much energy. So we're going to use the heat flux equation to calculate this. Q is equal to the mass of the iron times the specific heat capacity of the iron times the change in temperature. Q is equal to mc delta T. So the mass of the block, we are told, is 1.49 kilograms. Let's turn that into grams, because I give you the specific heat capacity in grams. So if you use the wrong units, everything's going to get muddled and we get the wrong answer. So 1.49 kilograms times 1,000 grams per kilogram. Put that in brackets. There's your mass in grams. Your kilograms are going to cancel. Your specific heat capacity is 0.4494 joules per gram degree Celsius. And that's going to allow you to cancel grams, you see. And then the temperature change is 137 degrees, because it goes from 155 down to 22 degrees Celsius. And that's going to allow you to cancel degrees Celsius. So your answer is going to be in joules, because everything else cancels. And you get 891. Okay, my writing is so messy that I can't read it myself. So sorry about that. Let me do the calculation over. I did this probably before you were born. Here. Yeah, look at that. Look at the date on that bad boy. It says 98. Oh, you can't see it. I'll show it to you. Yeah, I made this handout back in 1998. That was before you were born, I think. 22 years ago. So anyway, what do you get? Where did I put it now? There it is. Okay. 1490 times 0.4494 times 130.
Caitlin, please call extension 6001. Caitlin, 6001.
133. And you get 89,057 joules of energy. Well, if you want to be a stickler, 0.598 joules of energy. Now, if we pretend that all these joules of energy were released over a period of half an hour, that's 30 minutes. 30 minutes. So released over 30 minutes, which is basically 1,800 seconds. How do I know that? 30, so it's 1/2, I'm going to say 0.5 hour times 3,600 seconds per hour. You should be able to figure that out without too much difficulty. 1,800 seconds. Now here's a little definition you should know, and if you don't, you're going to know it now. 1 watt equals a joule per second. Okay, the watt is a joule per second. So your 1,500 watt hair dryer uses 1,500 joules of energy per second when you have it on the maximum setting and you put it on hot. That's about 2 horsepower, by the way. That's the maximum output your little outlets can do. Your household outlets have a limit of about 2 horsepower. If you do more, you blow the fuse. There's a fuse in your fuse box downstairs that prevents more than 2 horsepower of energy to be pumped through the electrical wires. I don't like to use the word pumped. It makes it sound like you're pumping water or something, but you know what I mean. It doesn't allow more than 15 amps of electricity to pass through the wires, because otherwise the wires start to overheat and then you can cause a fire. So they limit it at the fuse box. If you go over that, something clicks and it turns off the power. And then you have to go back downstairs and click it on again. In the old days, they just used to have this little button with a thin metal strip. And the metal strip was designed so that if too much electricity passed through it, that part would just melt and it would stop the flow of electricity. Then you'd have to go down and take out the fuse and put in a new one. Nowadays, we just have breakers, which are made of bimetallic strips, where one strip of metal is different from the other strip of metal. And when you heat one up, it bends the strip the other way and it clicks, so that you turn off the circuit. So anyway, how many watts is that? All this energy flowed in that many seconds. So we can find out what the average wattage is going to be. Of course, you're not going to get an instantaneous wattage, because what happens when something is warmer, it gives off the heat faster. So as it's cooling down, it gives off less and less heat. But we don't care about that. We just want to find out an average value. So the wattage is going to be 89,057.598 joules divided by 1,800 seconds. So your little brick of metal cooling down in a period of half an hour puts out about 49.476 watts. Or you could, we have about what, 3 sig figs here? 2 sig figs. So we're going to say 49 watts. Which is not much, but you know, if you have it under the covers, it's enough to keep your feet warm. So that's good for today, I think. Now you're going to watch part 5, and then you're going to make notes. And tomorrow I will continue with the thermodynamics content. I'm going to upload this video that I recorded from the phone as well, so you can rewatch this same lecture, because apparently it doesn't record very well on Google. And what else? Okay, I should do attendance. Kyle? Okay. Stella? Daniel? Shade? And Ramella? Stephen? Persis? And Nancy? All right, guys. Have a good afternoon, and we'll see you tomorrow. Bye-bye.